Welcome back to Standing on the Shoulder of Giants. In 1964, Arno Penzias and Robert Wilson were frustrated. Like Karl Jansky more than 30 years prior, they were physicists working at Bell Labs. Like Yancey, they were working on a new cutting-edge radio antenna. And, like Yancey, they were having trouble getting rid of a faint but persistent hiss in their data. Once again, that hiss proved to be an incredible discovery. Yancey had picked up radio waves emitted by the centre of the galaxy with his radio antenna, a discovery that marked the beginning of radio astronomy. Penzias and Wilson had found something even more extraordinary. Their radio antenna was detecting light that had been travelling through the universe since shortly after the Big Bang. Arno Penzias was born in Munich, Germany in 1933, and his life may well have been saved by a radio signal. At the age of 6, he and his brother were among the 10,000 Jewish children evacuated by the United Kingdom, a rescue operation known as Kindertransport, after a broadcast was sent out via BBC Radio asking for foster homes for children fleeing Nazi-occupied parts of Europe just before the start of World War II. His family was eventually reunited in New York City, where he earned an undergraduate degree in physics from the City College of New York and a doctorate from Columbia University. Robert Wilson, a few years younger than Penzias, was born and raised in Houston, Texas, spending time in the oil fields where his father worked as a chemical engineer. He describes himself as a middling student at high school, but followed his father's footsteps to Rice University. He earned a degree in physics before moving on to Caltech for his PhD. Penzias and Wilson met at a conference in 1962, when Penzias was already working as a physicist for Bell Labs in New Jersey. In the decade since Karl Jansky's discovery, Bell Labs had remained a top-notch site for physics research, driven by their overarching goal of pushing the limits of long-distance communication. Wilson joined Penzias at Bell Labs, and the two began working with the Holmdel-Horn antenna, a 20-foot radio detector built atop Crawford Hill in New Jersey. It had originally been used to capture radio signals from an early NASA communications satellite. When the communication project ended, Penzias and Wilson took over use of the antenna. They hoped to repurpose it for radio astronomy and study how radio signals interacted with Earth's atmosphere. However, when Penzias and Wilson first started pointing the New Jersey antenna at empty patches of sky, a standard step to calibrate the detector, they kept picking up the same background noise, a kind of microwave static. What's more, unlike Karl Jansky's detection of radio waves from the centre of our galaxy, this static hiss seemed to be coming from everywhere, popping up in their data no matter where they pointed the telescope. Astronomers are used to this sort of static. You may remember from a previous program that everything from car engines to fluorescent lights can produce radio signals that interfere with telescopes. Penzias and Wilson immediately began examining their antenna and its surroundings, suspecting that their persistent microwave signal was actually just some local signal interfering with their work. They ruled out cars on the Golden State Parkway and stray signals from a nearby military base. They even questioned the local birds. 2 pigeons had set up house in their antenna, leaving behind what Penzias politely referred to as a white dielectric substance. The 2 physicists gamely climbed into the telescope and wiped it clean. Still, the microwave static remained. They looked for variations in the static across the sky and found none. They measured the static for an entire year, in summer and in winter, but to no effect. This microwave static appeared to be clear, consistent and real. But what was it? Ironically, just about 30 miles west, another team of physicists at Princeton University had recently begun building a microwave detector with the sole goal of finding and measuring the exact signal that was plaguing Bell Labs. Drawing on nearly 2 decades of research and theories, they dreamed of finding a faint, consistent microwave hiss, in the hopes that it would prove to be a long-predicted signal that we know today as the cosmic microwave background. Just after the Big Bang, our universe looked very different than it does today. If we could go back in time and look around, we'd see, well, not much. The universe in those early days was incredibly hot and opaque, filled with a miasma of free electrons that blocked the path of any photon or particle of light that was trying to travel. This meant that photons couldn't easily travel across the universe. Instead, they would bounce around in this sea of free electrons like something trying to push through a crowded room. However, according to the Big Bang theory, the universe would be rapidly expanding at this point in the aftermath of the Bang itself, cooling as it went. After about 300,000 years, the universe cooled off to a chilly 3,000 degrees Kelvin, colder than the surface of the Sun, but still hotter than any modern-day blast furnace, allowing the electrons to team up with the photons and make the universe's first atoms. Since this tied up the electrons, the universe became less opaque and photons were free to go rocketing from one end of the still rapidly expanding universe to the other. If we could go back in time to this moment, we'd see these photons appearing and beginning their trip across the universe as a faint, deep red glow. We know that these photons would look deep red thanks to a principle known as black body radiation. If a theoretically ideal body that absorbs all electromagnetic radiation is warmed, the laws of thermodynamics tell us that the black body will emit energy, and that the energy it emits will be directly related to the object's temperature. This energy is emitted as photons, the elementary particles that make up light. Photons emitted by a warm object will carry away very specific and discrete amounts of energy, measured by scientific instruments in terms of different wavelengths of light, which we could perceive as different colours. We can write out the relationship between a photon's energy, wavelength and speed using the equation E equals h times c over lambda. E here refers to energy, while c refers to the photon's speed, the speed of light, and lambda refers to the photon's wavelength. Remember that, to us, longer wavelengths look red, while shorter wavelengths look blue. The only thing left to account for in this equation is that little h. This is Planck's constant, named after Max Planck. Max Planck was a German physicist who, in the late 19th century, made groundbreaking discoveries about blackbody radiation, mathematically describing how photons work and how warm objects emit them. You can see how blackbody radiation works, and why we know these photons travelling through the universe after the Big Bang would have appeared deep red if you play with this equation. Blackbody radiation tells us that, since Planck's constant and the speed of light both stay the same, if we raise the value on the left side of this equation, the energy, we have to lower the value of the wavelengths in the denominator to keep the equation balanced. This means the wavelength has gotten shorter. In other words, a high energy photon will look bluer. What does this have to do with temperature? For that we need another discovery of Max Planck's, this one known as Planck's law. He was able to mathematically write out how the energy emitted by a black body would depend on its temperature. If we look at Planck's equation for black body radiation, you're probably thinking, what the? But don't worry, we don't need to do much with it. We just need to find the three properties we're talking about here: energy, temperature and wavelength. The algebra of this equation tells us that if we raise the object's temperature, we raise the amount of energy that it emits and decrease the wavelengths of light that carries away most of the energy. This can be drawn as a diagram. To show a spectrum, we need to draw a graph plotting wavelength on the horizontal axis and brightness on the vertical axis. Plotting a hot object, say something like our Sun, with a temperature of about 6,000 degrees Kelvin, will emit light according to Planck's law. This will give us the Sun's blackbody radiation curve. The area under the curve tells us how much energy the Sun is emitting, and the shape of the curve tells us how much energy the Sun is emitting at different light wavelengths. We would see that most of the Sun's energy is being emitted as light with a wavelength of about 500 nanometers, which we perceive as a yellowish green light. Now we can try the experiment with something hotter. Let's pick Sirius, the brightest star in the night sky, with a temperature of nearly 10,000 degrees Kelvin. When we use the Planck equation to draw out its blackbody radiation curve, we get a curve with much more area under it, which tells us the star is emitting more energy, and a curve that peaks at much shorter wavelengths. This is why to us Sirius appears as a bright blue-white star. Finally, let's consider our 3000 degree Kelvin temperature in the early universe, and the light emitted in the early universe that was beginning to travel through space. Its blackbody curve has less area under it, so we know it's emitting less energy, and it peaks at a longer wavelength, emitting most of its light as infrared photons. Light near these wavelengths would appear as a faint, deep red glow to the human eye. These infrared photons that began speeding through space 300,000 years after the Big Bang are still travelling through the universe, and some of them are just now arriving at Earth. These photons, however, have been dramatically redshifted thanks to the expanding universe. We can also think of this as the radiation from the early universe cooling off, corresponding to a much colder blackbody temperature today of only 2.7 degrees Kelvin. That's minus 455 degrees Fahrenheit. If we go back to the laws of thermodynamics and blackbody radiation, that means the photons we detect from that era should have much longer wavelengths, observable as microwaves. The idea of a cosmic microwave background can be traced back to Ralph Alpher and Robert Herman, two American cosmologists who first proposed the idea in 1948. Working forward from the Big Bang and using Edwin Hubble's famous equation and constant for describing the expansion of the universe, they estimated a blackbody temperature of 5 degrees Kelvin for the background radiation of the modern universe. It would be over a decade before several scientists either rediscovered their work or made their own predictions on how this background radiation could be observed, with estimates moving ever closer to the radiation's true temperature of 2.7 Kelvin. One of these scientists was a physicist named Robert Dicke, who had studied the question of the temperature of space for years and invented the most widely used microwave detector design while working at MIT. By 1964 he was at Princeton and hard at work on a painstaking scientific mission to search for and hopefully detect the cosmic microwave background, and with it the first robust observational proof of the Big Bang. Several colleagues at Princeton had joined him in the search. Jim Peebles had recently written about how to detect and identify this radiation and was preparing to publish his results, while David Todd Wilkinson and Peter Roll began building a top-notch microwave detector following Dicke's design. This was, after all, the best design for microwave antenna in the world, a design shared by the Bell Labs antenna just up the road. Penzias and Wilson soon realized that what they had found at Bell Labs could potentially be this theorized cosmic microwave background, and placed a call to Dick at Princeton to learn more about the phenomenon and share what they had found. It just so happened that Dick was in a meeting with his colleagues when the call came through. After hearing what Penzias and Wilson had found, he hung up, turned to his fellow physicists and said, "Well, boys, we've been scooped." To be scooped in science is to have another team discover something you're looking for, to figuratively scoop a new result right out from under you. It can be a crushing disappointment to see years of effort fall short in a field where most recognition goes to the first scientists who make the discovery. Or, in the case of the Princeton team, a moment of excitement when finally coming face to face with a much anticipated new result that was ready to be explored and analysed, even if they weren't the ones to make the discovery. The Bell Labs and the Princeton groups quickly joined forces and submitted a pair of groundbreaking papers to the Astrophysical Journal. Dick Peebles, Roll and Wilkinson's paper laid out the underlying theory and predicted properties of the microwave background. It was followed by Penzias and Wilson's painstaking description of their microwave signal and how it was detected. Together, the two papers represented an immense leap forward in science's understanding of our universe's history. The discovery was recognized with a Nobel Prize in 1978 for Penzias and Wilson. Every year the Nobel Committee awards a maximum of 3 physics prizes, and the third physics prize that year was awarded to an unrelated field. Penzias and Wilson's observations had arguably been the crucial catalyst that led to the cosmic microwave background's discovery, and wholly deserved the Nobel. But the prize's limitations meant that the contribution of Robert Dick and his group went unsung. After its discovery there was a surge of interest in observing the cosmic microwave background, in the hopes that the properties of this radiation could be used to untangle long-standing mysteries about our universe. At a glance, the cosmic microwave background fit wonderfully with the predictions of the Big Bang Theory and physicists' model of the universe. It seemed to be spectacularly uniform. Astronomers detected the same hiss in every part of the sky, and everywhere they looked this radiation corresponded to the same black body temperature of about 2.7 Kelvin, rather than appearing hotter in one direction and colder in the other. This agreed wonderfully with one of the core tenets of modern physics, a cosmological principle, stating that at large scales the universe should look the same from every location, what we call homogeneity, and in every direction what we call isotropy. That said, Penzias and Wilson's early observations may have been enough to prove the cosmic microwave background existed, but they didn't capture enough fine-grained detail. A detailed study of the cosmic microwave background was, in fact, crucially important, since the Big Bang Theory actually did predict small inhomogeneities in the universe, tiny ripples in the earliest fractions of a second after the Big Bang that eventually led to the formation of the vast structures we see in the universe today, galaxy clusters and superclusters and enormous swathes of dark matter. The fingerprints of these little fluctuations should be observable in the microwave background in what we call anisotropies, small hot and cold patches observable in different directions in the sky. What Penzias, Wilson and Dick knew all too well was that detailed observations of microwave signals could be extraordinarily difficult. Eliminating every other stray source of noise or interference on the planet in order to detect the steady and whispered signals of the cosmic microwave background was an immense challenge. To get a good close detailed look at this faint radiation, telescopes needed to be both as powerful as possible and remote as possible. Space-based telescopes proved perfect for this work, and in 1982 NASA began building the Cosmic Background Explorer, or COBE, a satellite carrying several instruments. One was a microwave detector that would make a map of any tiny anisotropies in the cosmic microwave background. The microwave detector's design and construction was led by George Smoot, who had previously designed detectors that rode aboard stratospheric balloons and high-altitude planes to study the cosmic microwave background. Another instrument on board COBE was a spectrograph that detected very long wavelength infrared light. The team that built this was led by John Mather, and it was specifically designed to measure the cosmic microwave background's all-important black body spectrum. COBE was originally designed to be launched by a space shuttle crew. Unfortunately, the Challenger disaster grounded all space shuttle flights, and COBE was ultimately redesigned, launched by an uncrewed Delta rocket in 1989, and placed into something called a sun-synchronous orbit. This orbit sent COBE around the Earth very close to the planet's poles, following the apparent motion of the Sun relative to the Earth and carefully orientated so that the satellite's instruments were always pointed away from both the Sun and the Earth. 1 year's observations would allow COBE to slowly scan the entire sky, mapping the cosmic microwave background and measuring its temperature along the way. The experiments designed worked spectacularly. In 1992, the COBE team announced that they had, in fact, mapped anisotropies in the cosmic microwave background. Their groundbreaking map of the cosmic microwave background was lauded as an immense scientific discovery, identifying the fluctuations that had been predicted by cosmologists and point back to clear evidence of the Big Bang. In 2006, George Smoot and John Mather were awarded the Nobel Prize for COBE's observations, the second Nobel recognizing research on the cosmic microwave background. COBE's all-sky image of the cosmic microwave background has continually been improved upon in the decades since. Another NASA mission, originally named MAP, or the Microwave Anisotropy Probe, was launched in 2001 to do exactly what its name suggested, mapping the cosmic microwave background in exquisite detail and building on COBE's success. This mission was renamed WMAP, WMAP, with the W recognizing David Todd Wilkinson. He had been one of the original members of the Princeton team building a Dick interferometer and hoping to measure the cosmic microwave background back in the 1960s, and he had gone on to work on the MAP mission's science team before passing away due to cancer just 5 months before the mission's first hotly anticipated data map was released. In the end, the WMAP data revealed the cosmic microwave background in exquisite detail, measuring minute temperature fluctuations smaller than 1/1000th of a degree Fahrenheit. WMAP observed the cosmic microwave background from an even darker and more remote location than COBE's sun-synchronous orbit. It was launched well past the Moon at a distance of 930,000 miles from the Earth. Near the end of its mission lifetime, it was joined there by an observatory operated by the European Space Agency, known as Planck, named after the same Max Planck who studied blackbody radiation. The Planck Observatory improved again on the maps of previous missions, releasing an astonishingly sharp all-sky map of the cosmic microwave background and its subtle fluctuations in 2013. Teams today have continued to analyze the results of these missions and use the data as a linchpin for measuring everything from the age and composition of the universe to the ever-elusive value of h0, the Hubble constant, These are the data that give a dramatically low value for the Hubble constant of 68, as compared to the immensely high 72 or so from studies using observations of nearby stars and galaxies. What began as a faint hiss that could have come from pigeon droppings has now become one of the most crucial signals being studied in astronomy today. From Dick's detector designs to Penzias and Wilson's discovery, and on to the observations by satellites like COBE, WMAP and Planck, work on the cosmic microwave background has shaped our understanding of the entire universe, from its size and age and earliest beginnings to the way it works today. Current research is still focused on investigating the cosmic microwave background for subtle but crucial signals. For instance, examining the background's electric field could reveal primordial gravitational signals from just after the Big Bang. The information hidden in the carefully studied anisotropies could help us understand the evolution of the early universe and the obscure physics happening in the vacuum of space. Finally, the cosmic microwave background has been combined with other groundbreaking discoveries to help us understand the fundamental makeup of our universe. While not all these discoveries have been recognized with Nobel Prize, the incredible science behind them and the heroes that have made them possible have contributed crucial pieces to our evolving puzzle of explaining the building blocks of our cosmos.